most beautiful inventions in mathematics is the Maclaurin series, which is a power series that allows one to calculate the approximation of a function f of x for input values close to 0. Again, I'll talk about this later, but let's talk about who invented it. It's a Scottish mathematician named Colin Maclaurin, who also made important contributions to geometry and algebra and other branches of mathematics. He's known for being the youngest professor in mathematics. He's Mr. Pi. He was a prodigy. True enough, he was a child prodigy. So we talked about the history of the Maclaurin series. Let's talk about the primary goal behind the Maclaurin series. The primary goal is to express a function f of x as an infinite power series. So what's an infinite power series, you may ask? It is an infinite collection of terms where the general term is a sub r x to the power of r, where r can vary from 0 to infinity. Now let's take a look at the requirements for a Maclaurin series. The first one being the function must be infinitely differentiable. That means you can differentiate how many times you want. And the second one is the fact that the rth derivative of f of x must exist at x equal to 0. Alright, so in order to express a function as an infinite power series, recall that infinite power series is an infinite collection of terms. We need to evaluate the constants a sub r, where r can vary from 0 to infinity. Then we have the Maclaurin series, and now let's get to work. Now we shall consider that infinite power series, which is just an infinite collection of terms whose constants we must evaluate. Let's evaluate the first derivative of f of x. Oh, it must be clear cut that f dash x is equal to the following. Let's also evaluate the second derivative of f of x. And since I want you to understand the real definition of the Maclaurin series, let's evaluate the third and fourth derivatives as well. Now that we've done that, let's evaluate each of these derivatives at x is equal to 0, starting with f of 0, which evaluates to a naught. Let's twist this a bit and write this as 1 times a naught. The reason will be apparent later on. F dash 0 is nothing but a1. Well, let's twist this and write it as 1 times a1. Let's follow suit with the second derivative, the third derivative, and the final fourth derivative. Now you'll begin to see a small connection between these. So let's find that out. It turns out that is 0 factorial times a naught, 1 factorial times a1, and the second derivative is 2 factorial times a2, and the third derivative is 3 factorial times a3, and the fourth derivative is 4 factorial times a4. Now I hope that you can see a very clear-cut connection between the derivatives and the right hand side. So let's generalize these into a general formula that we will use to evaluate the Maclaurin series. So I hope you can see that the rth derivative evaluated at 0 is equal to r factorial times ar, for all r being an element of the non-negative integer set. Let's manipulate this and subject a sub r. And there you have it, the first step towards the Maclaurin series. Once again, we shall consider that infinite power series, f of x, which is just an infinite collection of terms. I'm sure that you'll begin to realize that this has a general term. You may ask, what's a general term? Well, the general term is a sub r x to the power of r, for all r belonging to the non-negative integer set. Hey, it's Mr. Pi again. Oh, he's asking what that symbol means. Well, that symbol is the symbol that mathematicians use to denote quote unquote for all. So that statement would read, for all r being an element of the non-negative integer set. Now that we know the general term, let's write the infinite series as the sum of the general terms. Why not make it more compact, and let's write it as a summation. Since we know the general term UR, let's substitute that for UR. Also recall that we know the formula for A sub R. So let's substitute that for A sub R. And there you have it, my dear friends. This is what you call the Maclaurin series. Well, will any Maclaurin series video be complete if I did not show you how to derive a Maclaurin series for the famous e to the power of x? So, there we have it. We need to find the infinite power series for e to the power of x. So, recall that the Maclaurin series is a summation of the rth derivative evaluated at 0 over r factorial times x to the power of r tends from 0 to infinity. So let's expand it so that we'll get a clear-cut idea of what we're supposed to find. Well, you will see right away that we need to evaluate each of these derivatives. So we need to evaluate the 0th derivative at 0, the first derivative at 0, and the second derivative at 0, and so on and so forth. So let's do that. So, well, it's obvious that the derivative of e to the power of x is e to the power of x. Oh, wait a second, it's Mr. Pi again. He's asking how is that? Well, actually, that's a really good question because many people take that for granted. So let me show you that the derivative of e to the x is e to the power of x. So let's start with the base definition. F of x is equal to e to the power of x. Let's take the natural logarithm of both sides. Well, it follows that the natural log of f of x is equal to x. Now let's differentiate both the left hand side and the right hand side with respect to x. So f dash x over f of x is equal to the 1. This implies that the derivative f dash x is equal to f of x. So there you have it. F dash x is equal to e to the power of x. So it follows suit that the rth derivative of f of x or e to the power of x is nothing but e to the power of x, as I just proved. Well, if that's the case, then we know for sure that any derivative evaluated at 0 will definitely be equal to 1, since e to the power of 0 is always 1. Now, let's reconsider that infinite power series I talked about. So here it is for e to the power of x. So now you begin to realize that we have found each of these derivatives evaluated at x is equal to 0. Since we have them, why not substitute them? So e to the power of x is equal to 1 over 0 factorial plus 1 over 1 factorial x plus 1 over 2 factorial x squared, and so on and so forth. And this is the Maclaurin series for e to the power of x. Well, what if you wanted to find Euler's constant? Well, substitute x is equal to 1. So, after you substitute x equal to 1, it follows that e is equal to the following expression, and there you have it. This is Euler's constant.